Okay, now let's begin our class. So I want you to keep your focus on those head. Now from now on, we want to estimate the states. Assume we give you the u and y without head. Those u and y here, the u, y are from measurement. All the head means you computed. All right. So, example. Now I'll give you example. So how can we, if I give you, I give you y for your lab, and then, okay, now I say, okay, give me your estimate states. And look at this example. Of course, here, I don't assume we have any error, measurement error. Assume the measurement error is free. No error at all. The same, I give you A, B, C, D. Assume A, B, C, D also exact. So assume A is 0, 1, minus 1, 0. B is 1, 1. Assume delta T is 90 degrees. That's what we assume. So delta T is 90 degrees. So we have cosine delta T equal 1. Sine delta T equal cosine delta T equals 0. Sine delta T equals 1. All right. Like that. And C and D, and this from that measurement. Okay. Sorry. I don't know why it's got that one here. My G, that's important. My G, my observer. Look at that. My observer cosine theta T, because that's 90 degrees, so that's 0. G is sine 90 degrees is 1, and cosine theta T is 0, so we have 0 minus 1. That's my observer gain. That's the gain. So as soon as I know my delta T, my time interval, my sample interval, then I have my gain. All right. Then that's delta T is minus 2 pi. Okay. So that's assume I have, that's my the system. Suppose that's my system, and this all my state. All right, and this I had x1 from this. I'm talking about this is my time history. This is my true state. I'm computing my true state here. My initial condition is 1, 1. My u is giving is 1 minus 1, 1 minus 1, 0, 0. All what I'm doing here are supposed to do from your laboratory. This is simulations. And then I have my y. That's my y. Let's assume this is also from laboratory. I giving you the y. I giving the u. And my measurement y is 0, minus 3, 2, and 1. Remember that. This is assume that from your laboratory, because I'm not doing my laboratory, I'm doing just my simulation. So I assume my initial state is my true initial state is 1, 1. My true u is 1, minus 1, 1 minus 1, 0, 0. After I done that, my true measurement y is 0, minus 3, 2, 1. This is all without head. That means my true one, the real one. My real one here, I assume no measurement noise, no measurement error. Also, I assume my A is perfect, my B is perfect, C is perfect, and D is perfect. It won't happen in our life, but in the textbook, yes, it will, right? So this is I assume that I use my computation to simulation to get my true y. That's my true y. That's my true y. This is my true initial state, and this is my true ABCD. Okay, so keep in mind that What we need is ABCD here, and we need U, we need Y. All right, now you watch the next one. Recall that my initial state is 1, 1. My true initial state is 1, 1. That's my true one. Then I look at my estimate. So the estimate requires ABCD. Assume I give you that ABCD. Of course, in real life, in practice, the ABCD not calculated from this kind of theoretical approach. You may get ABCD from what? From your system identifications, from other methods. But now, assume I give you ABCD. But look at that hat. My X hat, I assume 0, 0 because I don't know. In real life, we don't know my initial state. I assume initial state 0, 0. If I don't initial state, the easier one, just assume they are 0, 0. I agree. Do you agree? I assume 0, 0. So I have U, 1 minus 1 minus 1 and dot, dot, dot. I have my Y, that's my true Y is 0 minus 3 and 2 and 1. That's true. Those information I know. My initial estimate state is 0, 0. That's assume. You can assume any value if you want. You don't have to be 0, 0. You can have to be 105. Any value you can assume that. All right. Let us look at my estimate Y. My estimated Y 0 is Cx0, that's from here, plus du0, du0 is 1, that's there. All right. Then that means 1, 1 is equal to 1. So Y hat, my estimate output, Y hat is equal to 1. But my true Y is 0. You see that? It's not the same as my true. My X hat 1 equal to AX0 plus BU0, that's U0 is equal to, is here, plus G, look at G. G Y hat 0 minus Y0, Y hat is 1 here. Y hat is 1 here. Y hat is 1 here. Minus Y0, Y0 is my true one, is 0 there. So 1 minus 0, my estimated 0, y minus my true Y, my measurement Y, my measured Y is 1 minus 0. So my state, my X hat state 1 equal to 1, 0. That's my estimate hat. Now you check your note, see if what is the true X1. 1, 1, right? So that's different. It's not the same thing, your estimate. All right, look at the second one, this Y hat 1. The Y hat 1 is Cx hat 1 plus Du1 equal to minus 1, 0. X hat 1 is from here 1, 0. That's 1, 0. Plus Du1, D is 1. Now your U1 is minus 1. So it's minus 2. But your true Y is minus 3. Your estimate had Y1 is minus 2. It's not the same thing. All right. That's okay. You know, we'll see what happens. Continue to look at the second step. X hat equal to AX hat plus BU1 plus G Y hat 1. This estimate hat 1 is here. Minus Y1, that's true 1. That's my measure one. So A sub in here times X hat 1 is 1, 0, 1, 0 plus G is 1, G is 0, 1, minus 1, and Y hat 1 is equal to minus 2, and my true Y1 is 3, is minus 3, so minus 3 is 3. Then my X hat 2 is minus 1, minus 3. And what is the true state? Check your one. What is the true state?
Minus 1.
exact the same thing. So it took 2 steps to get your estimate exact the same as your true one. Only 2 steps. So you have only 2-step error, that's 0 and 1. Starting from the 2, the x hat 2, then you get exact the same as your true one. How about your y hat 2? Y hat 2 is cx2 plus du2, and then that's u2. The y hat 2 equal to 2, that's the same as this one, 2 here. So after the second steps, you get exact the same state, you get exact the same output. Your estimate state and your estimate output are identical to your true state and your true y. Don't you think that's a magic? If you don't believe me, you can change this 0, 0. You can change to be any value, 10,000 by 1. You will get the same, exactly the same as this one, just on a 2 step. Doesn't matter what kind of value, initial value you get. Any value. As long as it's like infinite. Any countable value, you will get this. So after the first step, first one, the time step 1, then start from 2, 2, 3, check your 3. X hat 3 is the same as your true state minus 2, 2? Yes, has to be. Has to be. Don't you think that's a magic? So if you get right, good, the observer gain G, then your estimate will be very accurate and very fast. And this is the fastest gain you can ever have in theory. So this is what we call Debye gain. That means in certain time steps, then you get exactly the same as your true one. Of course, we assume here we don't have any error. We don't have any measurement error. We assume ABCD are perfect, right? Which won't be the case in a real world. So you can see the power of the observer. In a control theory, you always need a good observer model for any control feedback, state feedback. We call state feedback. If you need a state to feedback to your system, then you will need observer unless you measure all the states. Then you don't need observer. But if you don't measure all the states, then you need observer to measure, to estimate those states you don't measure. For example, like this case, I use only what the accelerometers, but we estimate what? We estimate displacement, we estimate velocities. So this X here, the first element, the estimate here, the first element is displacement, the second element is velocity. But your sensor is accelerometer. Any questions?
What was the physical meaning of this observation?
The physical meaning? The physical meaning is, well, just what I say, that if you don't measure displacement, you don't measure velocities, then how can you get information about your measurement, about your displacement and velocities? Assume you have only accelerometers. Then of course you can integrate to get your velocity. You can integrate again to get your displacement. That's one way to do it. Another way to do it is you know the model. then you can, based on this model information, ABCD model information, and use this observer equation to estimate your states. Assume you don't know anything about your initial state. That's the key point. The key point is I don't know my measurement state and my initial condition. If I know my initial condition, then all steps will be identical. Okay. If I don't, then you will lose some states. That won't be good. But even the state x hat 1 and x hat 2, even the state x hat 1 is not accurate, but it can be used for feedback. All right. That's how there's a theory to tell that use state observer to estimate states, even they are not true state, is allowed to use for feedback. That's important. So observer, just name observer means observe. My model will be able to observe the states. That's a physics. That's a physical meaning. I depend on my model to compute my states. So that's your homework 6B. Just ask you to do these kind of steps. So for you to have your own feeling. And so your 6B, you can use any x hat 0 there. You can use any x hat. If you don't believe me, you go home and you change the non-0, 0, then you will get exactly the same thing. The first two steps there won't be the same thing, but starting from x hat second 2 will be all the same, because that has to converge to the true states in the second steps. Of course, if the system is not 2 by 2, then to solve G is not that easy. All right, and there's some method to do that. All right, any more questions? No? Then we go to next steps. Then let us talk at the final difference model. Now at this moment we learn the second order equation of motions. We learn the first order equation of motion. We learn the discrete model, discrete time model. We learn observer model, right? So we have 5 different models. They all represent the same thing, but so any one system, you can describe the system behavior by all different models. You can describe the system behavior by second order equation of motions. You can describe the system behavior by the first order equation of motions. You can describe the same system by discrete time model. Now, you can also describe your system by we call finite difference model. And they all related. Now, which model is supposed to use depends on what applications you want to do, or depends on your objective, your control objective. If you have a different control objective, then you use different methods, a different model. All right, we have a different model. The input-output relationship, I already showed you this. Yk equal to beta k u0 plus beta 1 k minus 1 u1, and what is the beta is defined from here. If you know A, B, C, D, and G, assume you know those observer, then you can write your model Yk equal to beta k u0 plus beta k minus 1 u1 and plus beta 1 uk minus 1 plus beta 0 uk. And if you look at carefully this, I don't have any state anymore. This simply show you the relationship between U and Y directly without using any states informations. All right, there's no state. State is not unique. U and Y is supposed to be unique because giving U, you got a Y. Giving U, you got another Y. But state, you can be any different coordinate system. The ABCD will be different if you transform your current state, current coordinate system to another coordinate system. Then your ABCD will totally different. It looks different. Your eigenvalue will be the same, but they look different. Okay. The advantages here is you are not dealing with any state, so you don't do any state estimation. You don't do anything like this. What does that mean? YK will depend on the past input, and past output. We call the past weighted input and weighted output, like a stock. The today's stock will depend on yesterday's stock, will depend on day before yesterday's stock. All right, agree? Your output, your stock output, and also your investment. If you invest more, you may gain more, or you may lose more. So this is why we call finite difference model. We have YK equal to this kind of the input and output relationship, and all in short, we can say we move all the Y to the left hand side, all the U to the right hand side, and this is the we call finite difference model, and this kind of model used in different disciplines. For example, they used very often in stock predictions, or very often in economy, and also now we use very often in engineering too, for this, particularly in adaptive control. For those control, you require to change your gain continuously. Then you use this one is better because you don't have to worry about the observer. Because the observer is already embedded in this beta and alpha, the observer G and B, A, B, C, D, all the model is all embedded in here, in beta and alpha. Okay, let's look at the an example. All right. Now, assume we pick up a G such that A plus GC parentheses P's power equal to 0 n by n, just like what I show you. I have a G such that A bar square equal to 0, 0, 0, 0, right? The same thing is if I can choose a G such that A plus GC P power equal to 0, 0, 0, 0, 0, 0. Now, this A is not just only 2 by 2. This A can be 10 by 10, can be 5 by 5, can be 20 by 20, can be 100 by 100. So this P will depend on your model size. For the model size only 2 by 2, then P can be only 2. For the size 5 by 5, P can be 5. Cannot be less than 5. For a size 10 by 10, then P must be larger or equal than 10.
Can be larger.
Can be larger. It cannot be smaller, but can be larger. Well, I will talk about that more. Now, assume we have that, then my finite difference model depend on what? My finite difference model depend on the past output and past input up to the P steps. In other words, if the P is 7 days, means my stock will depend on the past 7 days stock information. That's it. We don't need the past 8th day. All right, understand now? So the past P days. That's good, right? You don't want to pass the year, right? That's too long, too far away. So this is very short model, much shorter than that. The if this is the K, if K is 1,000, this K is 1,000. That's no good. But here it doesn't depend on K. It depends only your size of A. So here, if you look at this carefully, now in the physical meaning means my output, my current output, will be function of the past output up to the P time steps. The same thing input. All right. So, but however, now I just like a stock. If this YK is your stock price, if this UK is your stock investment. Now you invest how much, then you will gain how much the output. Of course, gain can be negative, gain, right? Can be lose, can be loss. All right, so this is a very simple model, and this is easier for a controller which require online controller. Means that I need only computed my output, my estimate output can be computed on the past P-step output. For example, I want to predict my tomorrow stock price. That's why K is tomorrow. K is tomorrow. Then what I need to do is I have to know the past 7 days the stock price and the past 7 days investment. Then plus tomorrow how much you want to invest. That's your UK. Then you can predict the price of stock for tomorrow. That's your YK. Understand now? All right. So that's we call finite difference model. So in terms of English, that means the current output is a weighted sum. The weighted sum means the alpha, and beta, because I have to weight my alpha 1 times the yesterday's the stock price, the alpha 2 times day before yesterday price. The alpha 1, alpha 2 will be the weight of your each, the past output. The same thing, beta will be the weight for the input. All right, the alpha, beta, the ABCD, your model and alpha, beta are related by this. It's related by A, B, C, D, and G. They have relationship. In other words, if you know A, B, C, D, and G, you will be able to compute the alpha and beta. But in practice, you don't have to do this. In practice, if you have input data and output data, you can use some system identification technique to identify your alpha and beta directly without going through A, B, C, D, and G. Any question about this? No. Okay. I believe that's clear enough. This is very simple one. Huh? I don't know why they come with this again. But anyway, let us look at this simple example again. This simple example is the same example as I use for observer. So I have A, B, C, D, and G. If I have A, B, C, and G, I sub those I use those A, B, C, and G and sub into in here. I can compute beta 0 and beta 1, beta 2, beta 3, that is C, B plus GD, because I know C, I know B, I know G, and I know D. I can compute I can compute B beta 1 becomes minus 1 minus cosine delta t. The beta t2 will be C A bar B G plus GD is cosine delta t. B3, look at kids carefully. B3, A bar square is 0, 0, so B beta 3 equals 0. Because A bar square equal to 0, 0, 0. Remember that? I also write here. That's my A bar here, right? 0, 0, 0, 0. The same thing, alpha 1 equals CG equal to 2 cosine delta t. Alpha 2 equals C A bar G equal to minus 1. And alpha 3 equals C A bar square. That square is 0, 0, 0, 0. So that's 0. So we don't have any alpha beta which is more than the A bar square. So beta 3 equal to 0, beta 4 equal to 0, beta 5 equal to 0, and so on. Alpha 3 equal to 0, alpha 4 equal to 0, alpha 5 equal to 0. So in summary, let me just go back again. In summary, finite difference model becomes this. Look at this. It's very simple finite difference model. Yk will be equal to 2 cosine delta t yk minus 1 minus yk minus 2. That's 2 cosine omega t is from here. The alpha 1, 2 cosine delta t minus yk minus 1, and alpha 2 times yk minus 2. So alpha 2 is minus 1. Then yk is beta 0 yk, beta 0 equal to 1. So beta 0 yk, it's beta 0 uk is uk because beta sub 0 equal to 1. Now beta 1 uk minus 1. Now beta 1 is minus 1 minus cosine delta t. So that's minus parenthesis 1 plus cosine delta parenthesis uk minus 1. And then beta 2 equal to cosine delta t. So cosine delta t uk minus 2. That's it. So this is my finite difference model. As soon as you have delta t, for example, 2 seconds, it's sub in there, then you got the whole complete model of your finite difference model. Any questions? No? Okay, great. So you will be able to do your homework later on, right? I will give you a homework about this one. All right, in summary, we learn in these chapters at least 4 different models. The continuous time model, including 2 different models. One is second order model, one is first order model. The discrete model we have on the first order discrete model. There's no second order discrete model. There's no such thing, second order discrete model. No. But keep in mind that this discrete time model is an exact model, is not approximate model of your continuous time model. Under the assumption that your input is a zigzag input, is a ladder type input. In other words, that input at each sample interval is constant. Assume that's true. Then your discrete time model is exact. Now, from that discrete model, we have observer model. Then we introduce the discrete time observer model. We did not talk about continuous time observer model. No. We talk about discrete time observer model. Because when we use computer to do feedback, that is a discrete time model. We also talk about finite difference model. And they all related to the A, B, C, D, and G. So all the model, any model can be used to describe the behavior of a system. Again, which model we supposed to use? It's case dependent. That means depend on your objective, depend on your system, depend on your performance, depend on your requirement. All right. However, if you use computer, you have to use discrete time model, observer model, finite difference model. Your continuous time model will be useless. All right, if you use a computer to control. Any question about this chapter?
Is there continuous time observer model?
They do, but it's not useful. It's useless because you need to use computer. So all the observer we today we see is a discrete time model. Okay, no question. I'm gonna take few minutes to talk about some important subject. All right, we need to change the file now. We need to close this guy. We need to close this guy, and we need to talk about the space, metric space. Okay, all right, change that. And it's this all in the in our website. And I forgot it. Maybe I mentioned to you already. If the file size larger than 1 megabits, I cannot upload it. The only thing I can give to you, just give you the download address. So if you don't see it from those handout, then you gotta go back to another page, and I give you the download site. All right, let's look at the. And I already upload this one. This one is not more than 1 megabit, so this is in our download site there. All right, now the subspace, metric subspace, because it's we need to use subspace the concept for the some control techniques development, and that's let us look at the subspace. Now I'm gonna talk about column space of a matrix. And the important idea is null space. So I'm going to define what we mean the null space of a matrix. There's the column null space of a matrix. There are row null space of a matrix. So I need the null space and null space of matrix, and either column null space or row null space or space of a matrix. The concept. So I'm going to take this chance to introduce you some of those concepts. Now, assume I have a matrix, and I have this matrix has V n column vectors. So this is column vector 1, column vector 2, column vectors n. So this column 1, column 2 to column n. So this is column vector and matrix. That's how we define column vectors. Column vectors. Like the eigenvector matrices, those are column vectors. All right. Now, the column space of a matrix is the set of all possible linear combination of its column vectors. So C1, V1, C2, V2, and Cn, Vn. So C is any arbitrary value. That's a scalar. That's not a vector. So if I if I have C1 to C2, Cn are all constants. So you give all possible value of constant C1, C2 to Cn from 0 to infinite. Any value can be negative, can be positive, can be real values, or here we talk about all real values. All right. If like that, then we create a space we call column space. Like for example, our real life, we are only 3-dimensional space. So our column, each column vector will be only 3 elements, right? That's like our coordinate. X coordinate is 1, 0, 0. Assume that's our column. Say 1, 0, 0. The second column, the y-axis, will be 0, 1, 0, right? The third one will be 0, 0, 1. Right, that's a column. So we have 3 columns. One is 1, 0, 0. The second one is 0, 1, 0. The third one is 0, 0, 1. So we have 3 columns. Then those 3 columns will create our column space. That's our universe space without counting time. I didn't talk about time yet. So our geometric space will be created by these 3 different columns. Agree? I call it geometric space. Right? You understand? Agree? Now, if we add time for another coordinate, means we have a 4 space. So our column will be 1, 0, 0, 0. The second column will be 0, 1, 0, 0. The third column will be 0, 0, 0, 1. The fourth column, the third column will be 0, 0, 1, 0. The time column will be 0, 0, 0, 1, right? That's the time. Now we become a 4-dimensional space. Of course, now it doesn't have to be 1, 0, 0, 0. No. Any combination of these 4 columns can be your coordinate. Your coordinate, you can transfer your coordinate, right? To become polar coordinate, become a Cartesian coordinate, all kind of different coordinates. So our human being, like you and me, we live in 4-dimensional space. 3 for geometric space, and 1 for time. So that's 4 space. Okay. However, in the matrix, you can be 5, you can be 6, you can be 7. So linear algebra matrix theory, they leave more space than we are. So this is what we call column space. So the column space of M by M matrix is a subspace of M dimensional called Euclidean space. The dimension of the column space is called the rank of the matrix. This is just terminology. This all in the matrix theory that they talk about this. All right, so keep in mind that we are talking about space, the column space. Column space created by these n different columns. Okay, let's move on. Example. That's the example. If I have A, only 2 columns. That's 1, 0, 2, 0, 1, 0. Then I have 2. So V1 is 1, 0, 2. V2 is 0, 1, 0. So my column space, my linear combination of V1 and V2 will be even. It will become to this. So giving any arbitrary value C1, C2, and C1. So look at this. The C1 and C1 they are dependent. The first one and the third one, they are dependent, they are not independent. So we create a column space, this, 2 columns, arbitrary. The rank of this is only 2. So this is only 2, just like a plane. Right? This is not geometrics. This is not 3-dimensional. This is only 2-dimensional space. So we create only by 2 columns. So this is the 2 Cartesian coordinates. So this is the column space is precise state of vectors x, y, and z, x, y, z in the 3-dimensional space, satisfying the equation is z equal to 2x. That's here, 2x. So now in the Cartesian coordinate, this is mean a plane. This is not a volume. This is a plane. This is just a plane. Just like our roll. Our roll is a 2-dimensional space, unless you have bridge go up over. All right. So that's the space. If you look at this, if I plot it out, x1, x2, and x3, you can see this is a flat plane. So you create a space, 2-dimensional space. So all the value inside here is inside that space. I assume that you don't want to live in the plane space, do you? That's no fun, right? So you can just move around in here. You cannot go there. You cannot go there. You can only go in this plane space. That's only 2-dimensional space. So that's this plane is infinite. It's not the finite space. It's infinite. All right, that's the example. So now here, null space. Remember that null space. The null space. What we mean the null space is the vectors, or all vectors such that x transpose A equals 0 transpose. For example, like here, the column null space is the orthogonal complement to the column space of A. I will give you an example soon. In other words, I have x1, x2, xn. Then this is all my column. This is each column here. Each column here. Take A transpose times x. So A transpose times x. So that means I multiply together equals 0. It's x1, x2, xn. All right. Then A transpose x equals 0 if and only if x is orthogonal to each of the column vectors of A. Right. They are orthogonal. Okay. And let's look at example. The same example we have there. x1, x2, xn. Now, A transpose times x1, x2, xn, x3, then multiply together becomes what? 1, 0, 2, and that means x1 plus 2x3, 1, x1, 2, x3. And the second one, x2, if I want to be 0, 0, then I have a vectors 0, 1, 0, minus 0.5, but I have an x1 here. X1 can be any arbitrary values. So this vector, 1, 0, minus 0.5 times any scalar x1, they are orthogonal to this one and that one. So the column space is that. The null space, orthogonal check, the null space, this times that one equals 0. So this one will be the null space basis vectors. This vector, orthogonal to that vectors, the first column vector and the second column vector. So this is the null space vector. Understand that now? So here I introduce you the column null space here. Well, it's time is up, so I'm going to stop here to stop the column null space. And next week I will introduce the raw null space and so on. Then after that we will talk about Paul placement technique, because Paul placement technique require to use null space. Okay, any questions? You know, then that's it. Next week I expect to go to NCU. Okay, see you next week.